let us start this lecture with a thought process. Creativity is like a spark that ignites the flame of innovation. In the last lecture, we have basically looked at the effect of the initial pressure and the initial temperature on the burning velocity, and we have seen that the pressure, particularly for certain mixtures or certain range of fuel air system, decreases the laminar burning velocity, but that is not true for all the range, and whereas the temperature enhances the burning velocity. And we have looked at semi empirical relationship to basically solve a problem, and also how we can handle the semi empirical relationship, taking care of the effect of inlet temperature and pressure, and also the dilution effect was embedded in that semi empirical relationship. Today we will be looking at the effect of inert additives or the dilution, you can say, on the laminar burning velocity, and here I have plotted the laminar burning velocity versus the percentage of fuel in mixtures. If you look at this arrow indicates the with the increasing of the inert content. Inert content means it will be any gas which will be act like for example nitrogen, helium, argon. So, I can look at that inert gas. This is maybe nitrogen, helium, argon or any other gases kind of thing. If you look at inert, then what is happening? This laminar burning velocity, let us say this inert is 0, like this is the thing, this is having a very high peak temperature here and peak laminar burning velocity here, and it reduces to the this is rich side, right, this is the lean side mixtures, and it of course decreases both the lean and the rich side. But when you increase this inert content, what you find that there is a reduction in the burning velocity, because the burning velocity as decreases, right. And beside this, if you look at, let us say this is the peak value here, and when you go for inert addition, then what will happen? It will be here. Then when it will be peak values of the burning velocity is changing, because let us say this is at this fuel air ratio, mixture ratio, and whereas here it is here. So, this is changing, that means it is going towards more leaner side. That is the one observation you can make. And another important things which we will be discussing later on, this is basically known as the flammability limit, like this is known as RFL, reach flammability limit, and this you can say basically this is lean flammability limit, right. And this is being narrowed down, like we see within this range the flame having certain finite burning velocity, that means it is flammable, but beyond this it is not flammable, right. It was the meaning, that means the flammability limit is being narrowed down. And as I told, there is a shifting of peak SL maximum, right. So, this is being shifted toward the lean side, and why there is a shift in laminar burning velocity peak? Because what happened with the addition of inert gases, the ratio of thermal conductivity and specific heat of the mixture resulting in change in burning velocity. So, we have seen that conductivity plays a very important role, and so also the specific heat. And specific heat, if you look at if it is being enhanced, then what will happen? The basically the temperature will be decreased for the same heat release rate, right. So, if the temperature will decrease, naturally the reaction rate will be decreasing, and if decreases, the burning velocity will decrease, right. And similarly the thermal conductivity. So, let us look at 3 diluents we are going for methane air mixtures, right. One is nitrogen, other is argon, other is helium, right. So, different, of course, here what we are doing in the upper one, it is the same diluent. Let us say if I take nitrogen, it will be one nitrogen, I am goes on increasing, but here what is being done, the percentage will be same, but the diluent will be different in this case, nitrogen, argon, helium. So, if you can look at that the observation that burning velocity with the helium addition is much higher than the argon, and the burning velocity for the argon is also much higher than the nitrogen. That is the observation you can make, and of course, there is a broadening of the flammability limit, particularly for helium, like if I consider this is the flammability limit, right. And that means when you go from helium to nitrogen, generally it narrows down the range of the flammability limit. That is another thing. So, question is why it is so, because what is happening, the thermal diffusibility of helium, right, is much larger than the argon, right. We have already seen this thing, like SL is basically root over 32 by 2, 32 by 9, alpha, this is your thermal diffusibility rho nu plus 1 F, this is we have already seen this formula, right. So, this is higher, right. And beside this, what you can see that rho u is basically inversely proportional to molecular weight, is not it? Rho u is proportional, rho u is proportional to molecular weight by the ideal gas law, right, as P is equal to rho Ru by MWT, right. So, rho is proportional to molecular. So, therefore, SL, if you look at SL is proportional to alpha, right, and molecular weight, right, and of course, this will be root, right, root will be there. So, if you look at that way, that molecular weight of the helium is much lower. If it is lower, then therefore, there will be increase in the laminar burning velocity as compared to the argon, and similarly the thermal diffusivity is higher. So, therefore, also it will be having effect. But when you look at the argon and nitrogen, you will find that it is have almost same thermal diffusibility. That means, it is not really changing by that. Of course, if you look at the argon will be having higher molecular weight as compared to the nitrogen, right, is not it? So, but here what is happening, the Cp, the argon being a monoatomic gas, the Cp value will be very low, right. For example, if I take at 300 Kelvin, Cp of argon will be something 0.52 kilojoule per kg Kelvin, and Cp of nitrogen will be 1.02 kilojoule per Kelvin, right, at 300 Kelvin. But of course, the argon being monoatomic gas, it will not be really changing much with the temperature, but however, nitrogen it will be changing with temperature, it will be increasing with the when the temperature increases. So, therefore, what will happen, the Cp of nitrogen being higher, then what will happen, to the temperature, the flame temperature. If you look at the Cp, basically if you look at the Q is equal to delta Sc by m is nothing but your Cp by Tf minus Tu. For the same heat, what happened, the Cp is higher. So, what will happen? If the same heat release or the same heat release per unit mass, right, what will happen? The Cp will be higher. That means the Tf, if Cp is increases, then Tf will reduce for the same Q, right. So, therefore, the temperature will be in case of nitrogen, when you add, will be decreasing, and this is having much higher effect. Why? Because it is e power to the reaction rate goes F e power to the RUT. So, therefore, this will be affecting much the reaction rate. As a result, that burning velocity will be reduced drastically, right. This is the argument what I am trying to give. So, therefore, argon attains a higher flame temperature as compared to the nitrogen. So, therefore, the burning velocity will be much higher, right. So, this argument one can look at it by explaining the experimental data or the observation what we got. And this is the effect of inert additives, and depending on that you can utilize it for your application. Now, we will be looking at basically the flame extinction, and question arises, what do you mean by flame extinction? Extinction means you will be basically dousing a flame, right, or dampening a flame, or you will make it extinguish, right. So, and it is having several applications, because the flame is a dangerous thing, one has to handle it carefully, right. So, however, we will have to contain the flame wherever possible, so that it should not affect the life and also the materials. So, flame extinction is very important in laboratories, in the of course the spacecraft safety purposes. The safety is very important. So, also the power plants, nuclear power plants, right, and the coal mines, and of course the aircraft safety, and your homes, like nowadays in IIT Kanpur we are having all the places fire extinguisher because of the safety issues. And the elevators, nowadays elevators are being used very much in the high rising buildings or skyscrapers, right, and there the fire safety is very important. Therefore, you will be using some flame extinguisher. And apart from that, several other places will be using, but this concept of the safety due to fire hazard is basically started long time back by Humphrey Davy. And when what he did is basically trying to extinguish a flame. It is not extinguish a flame, it is not allowing the flame to come out of a lamp, right. In this situation, what you will have to do, basically flame will be there, but it should not go beyond certain limit. What I will have to do? I will have to basically use that, won't allow the flame to pass through the narrow passages, which we will be discussing about that, like what are the size of the narrow passages through which the flame won't propagate, although the fuel and oxidizers within the flammability limits available. That means fuel oxidizer mixtures within the flammability limits are available, but flame won't go. That is the idea. So, this idea was basically employed long time back for the mine safety, and by the Sir Humphrey Davy, and he has developed a safety lamp. And keep in mind there is a controversy. Actually, this person is a very scientist, is one of the scientists, and there is another person who is not a scientist, was a uneducated person, but he made that lamp previously before the Humphrey Davy. but of course he lost the battle, and then people know that he is the person, and I really do not know what is the truth, right, whether that fellow did or this fellow did, but anyway he couldn't explain to the Royal Society at that time how it is working, right, but this person Devi could explain. If you look at, this is the lamp, and this is the a kind of a net, kind of a screen which is available, metallic screen, like metal screen you can say, and that won't allow the flame to propagate, although the around this thing will be the fuel air mixture will be there, particularly in the mines, there will be some gases due to pyrolysis and other things will be taking place, and some oxygen will be there, right, and that mixed, and that may if we are taking a lamp into the of course at that time, if you take a lamp that was which is burnt, which is basically made out of a kind of a weak flame, or the flame device or the combustion device, then naturally what will happen, it will spread the fire. So that is a very important breakthrough what happened, and then it is being done, and this is the screen which will help. And if you remember that we basically use this kind of a screen, metal screen particularly to stabilize the one dimensional flame, I had discussed earlier, right. And the flame extinction is very important, but question arises how we can do. There are two ways it can be done. One is of course the thermal effect, because we know the flame is self propagated because of fact that heat being transferred to the preheated zone, and then preheated zone will be attaining the self ignition temperature. As a result, the combustion will be self sustained, right. So if you reduce the heat, if you allow the some heat transfer to take place, that means heat loss will be much higher as compared to the whatever the heat being released, then flame will be extinguishing. That is one way. And another way is of course you can add, see this thermal effect is basically you can look at some water, you can take some water addition, and then what will happen, the Cp of the water is very high, so that it will be taking out the heat whatever being liberated. So that is the way it will be, flame will be can be extinguished, and that is which is a common way of doing it. Beside this there is a chemical reaction which is going on, right, and that can be the chemical kinetics during the chemical reactions can be altered by adding some halogen, some other constituents which will be affecting the kinetics of the chemical reaction. So by these two ways one can think of basically using extinguishing a flame. So you might be knowing that like wherever there is a flame we use also nitrogen gas, right, that is basically it will be acting as a diluents or the thermal effect, and whereas some halogen, some other constituents you can use. And this is the flame extinction. There will be also flame enhancement which is just opposite, right. That means it will be other one, you will have to minimize the heat losses from the flame, right, that is the one way. And another way that you add some additives which will be help in enhancing the chemical reactions, right. So that is just if you look at, one is positive aspect by enhancing the combustion rate, like we do use some additives like metal powders and other things are being used in your liquid propellants or the liquid fuel to enhance the reactivity of the propellants. So similarly in solid propellants and other places people do use it. And now coming this thing, we need to understand the flame quenching. So as the name indicates, quenching means what? Like basically it is the dousing a flame or dampening it, right. And how we can quench the flame is a very important question we need to ask. For that we need to understand what is happening inside the flame. We know that for a flame to propagate, right, certain energy being released due to the chemical reaction, and that maintains a high temperature. In other words, this heat transfer, heat release during the chemical reaction will be transferred to the preheat zone, and then the fuel air mixture will be basically enhanced and reach the auto ignition temperature such that the combustion will be taking place. And if heat loss can be increased by decreasing the passageway, right, because if in a tube, let us say there is a tube here, right, and there is a flame which is moving, right, and then this is the wall, right, and this is your tube, fuel and air mixture. It can be oxidizer also, right, it can be oxygen. So, these losses, heat will be lost to this, right, something heat loss. If this can be enhanced, right, then what will happen? The reaction rate will be reduced, because the heat release, whatever it is being generated, heat being released during the chemical reaction of fuel air mixture will be, heat will be released, reduced because of heat transfer through the wall, right, heat loss I can say. So, as a result, there will be resulting low reaction rate, right, and if it will be such that it will not be self sustained, then naturally there will be flame extinction. In other words, the energy release rate reduces due to the drop in the temperature, right, when the temperature drops below the self ignition temperature, right, then there will not be any heat release, right, and that leads to the flame quenching. That means, if you look at, if we summarize, basically what is happening, if you enhance the heat loss from the flame to its surrounding, like such that the temperature will be below the self ignition temperature, so that it won't be self sustained, because combustion means what? Even though you are taking out the ignition energy source, still combustion is going on. Ignition is just meant to initiate the combustion, after that it will be self sustained, right. So, therefore, the heat loss plays a very important role for quenching the flame, right. Question is how we will conduct this experiment to find out quenching. For that, we what we do, we will define a definition, that is quenching diameter or the distance, and that will dictate whether the flame will be quenched when it will pass through that. For that, we will have to conduct experiment. What we will do, we will take a tube, right, of diameter something, let us say d, right, some diameter, and this is fuel plus oxidizer mixture, and there is some kind of a flame is established, right. What you will do, you will now suddenly close this valve, that means you stop. So, if you stop this valve flow, right, which is going through this, what will happen? The flame will trying to travel inside this tube. This is a tube, right. So, it will be coming inside or not, flame will be moving inside with certain velocity. So, when it will move inside, then it will see this wall, like flame may be somewhere here, right, it may be flame will be here. As a result, that heat losses will be there, right, there will be some heat loss, and these losses will make the reduce the laminar burning velocity. If it is coming towards 0, right, then what will happen? Flame will extinguish, right. What I will do, I will take this diameter and see that flame is coming in, and this, of course, when the flame enters into the tube, we call it as a flashback, right. This process is known as flashback. and let us say D you have taken let us say 10 mm, right, for a methane air mixture, right, at phi is equal to 1. Of course, the initial temperature 298 Kelvin, pressure is 1 atmosphere pressure, we are conducting experiment. Then what I will do, I will take a small tube, like let us say I will reduce into 5, the D is 5 mm, right, and again I will conduct this experiment, right, that is fuel plus oxidizer and phi is equal to 1, right, I can write air will better, right. Then again flame is coming and then it is propagating, right, with a certain velocity SL. So, it is passing through it, that means it is not quench, right, it is not quench. Now, if I reduce to let us say it is something D is equal to 2 mm, right, flame is established here, but however, when this fuel and air phi is equal to 1 is stopped, then flame is entering here, but it may be moving to some extent, but the SL is coming towards 0, after that it will not move, flame is extinction. That diameter at which flame will not propagate, right, inside the tube, metal tube, where the heat transfer will be taking place. Why I am insisting on metal? Because heat transfer will taking place, then it will not propagate, it cannot propagate. That diameter we call critical diameter or the quenching diameter. That means the quenching diameter is the critical diameter of a circular tube below which a flame cannot propagate, right. And similarly, I can conduct this experiment in a 2-dimensional burner, right. For example, if I take this is a tube, right, tube means it is a something like this tube, right, and the 2-dimensional means it will be like a burner like this, tube like that, right, where the fuel and air mixtures, right. So, this is basically 2D flame, this is basically 2-dimensional flame, and similarly we can define a quenching distance, right, for a 2-dimensional flame. This is a 2-dimensional burner. Are you getting the circular and the 2-dimensional, right? Flame will be like this, these are the basically flame surface. So, and let us look at the quenching data for various stoichiometric fuel air mixtures. If you look at that, the methane air where the SL is around 40 centimeter, the quenching diameter is 2.5 mm, and of course, when it is replaced by air is replaced by oxygen, it became very small. Why? Because the burning velocity is very high. And similarly, for a propane air, this is 2.2 because burning velocity is higher, so it is lower than little bit. And if you consider the hydrogen air, right, it is the burning velocity is very high, 210, and it is a very small values. And if you go to oxygen, it is again reduced further because the burning velocity will be higher. So, with this we will stop over. In the next lecture, we will be looking at how this quenching diameter will be related to the laminar burning velocity using a very simplified analysis, right. So, we will do that in the next lecture.